Our speaker this afternoon is Terry Speed from the Commonwealth Scientific and Industrial Research Organization in Canberra. And Dr. Speed is soon to take up a position at the Department of Statistics at the University of California at Berkeley. He has been interested in the analysis of variance and the algebraic points of it. Recently, as you may have noticed from his papers, part of it is the question of why we would be interested in carrying out an analysis of variance when we choose to do so, and what we are really doing when we are carrying out an analysis of variance. And his talk today is along the same lines, it would seem to me, but we'll find out soon. The title is Generalized Variance Component Models, and here's Dr. Speed.
Thank you very much, Friedrich. Can I be heard just like this, talking, or should I use the microphone? Because I would have to talk like this, very close to it. I'd rather talk and walk around. Okay. Firstly, let me say that it's a very, very great pleasure to visit Tampere. I've been associated with some statisticians in Finland for a long time, since, well, almost about 20 years ago when I was an opponent at a PhD examination. And I've been opposing Finnish statistics continuously ever since. But I never had the opportunity to come to Tampere. In 1978, I stood on the station for 5 minutes. So then we went on to Helsinki. So it's a great pleasure to get off and be here for a while. And of course, it's a great honour to be invited to this second International Tampere Conference. What else? I'm talking about generalised variance component models. And it's something that I should make an initial apology. I don't hope to be able to convey too much in half an hour, but I hope that I might at least convey some interest and stimulate you to read some of the classical works, and maybe if you find that interesting, you might even read some of the neoclassical works. Oh, it's a great pleasure to announce the... I have a wonderful device here, probably made in Finland. I think of it as a symbol. Anyway, this will enable me to avoid pointing the finger. Okay, well, I owe this to the Department of Statistics at Helsinki University. So, my story begins by making the observation that variance component models these days are almost always these things that I've described here. I'm going to block people if I stand here, aren't I? With independent, normally distributed effects in linear models. And I think it's important for younger people who weren't around in the 30s, the 20s, to realise that this wasn't always so. That is to say that, in fact, if you look into the early work on, well, on the problems that we now address with variance component models, Fisher's work in the 20s, mainly in his book, Statistical Methods for Research Workers, number of papers by Yates, Neyman's papers on randomisation models, very interesting early work, again by Pittman and Welsh on randomisation or permutation models. Very nice, but perhaps well-forgotten paper by Daniels, which really crystallised some concepts of components of variance. And then later work by these authors here, Kempthorne and a stream of PhD students at Iowa State, Cornfield and Tukey, in a very interesting but perhaps not as influential paper as it should be, and later work by Nelder. Hardly any of these people have linear models with independent, normally distributed random effects. And I think I think there are good reasons why we should perhaps look at those papers again and wonder whether the trend these days is entirely progressive. I mean, of course, you could say we've made great advances. We now have linear models with independent normal effects. We don't have to worry about sampling or randomisation or permutation distributions. And I guess part of my talk is that I'm not thoroughly convinced that's a great advance. It might even be worth looking back. So this is an outline of my talk. I've got to use this somehow. So let me stand back. I'll mention very briefly some of the uses of variance component analysis. After all, it's worth thinking about what we're doing it for. What I mean by generalised models, but very loosely, that will mean models that aren't linear models with independent normal effects. What is a component of variance? A brief comment about that. Then I'll talk very briefly about some old approaches to some old problems that people will have forgotten. And finally, comment on what I describe as the problem of unbalanced arrays, which perhaps might be the reason why most of the discussion that we see these days is within the context of the normal additive models. That the other ones are rather hard to deal with. But rather than give up, I think it might be worth thinking about. Oh, so that's the plan. There's not very much mathematics in this, but Friedrich was kind enough to refer to some papers I've written. If you are interested in mathematics, there's more than you would want to know in those papers, and I refer you to them. Well, the first topic is a very humble topic, but in day-to-day work on analysis of variance, it still gets used. The estimation of a population mean, where populations are already things that don't get mentioned much these days. But when you go back to the work in the 30s and even the work in the 50s, the concept of a population is rather more explicit than this mystical thing that underlies normal distributions, which are never really populations in any sense that we can think about, so-called infinite or hypothetical populations, whereas a lot of this work goes on in a context where there are real populations. Okay, well, I won't elaborate on this very much, but a standard problem is to take some observations which have a number of strata of variability, perhaps just the simplest stratified population, and you're interested in the average value of the object and how many groups and how many individuals within the groups you take is open to you to choose. So you want to know the optimal allocation. If you're sampling for some sort of insect infestation on leaves, on trees, you want to know how many leaves you should take and how many trees you should take, or how many forests you should take, how many stands. So there are all sorts of problems there, and they go back to the very earliest days. And, well, I'll refer back shortly to whether we need linear models with additive, independent, normal effects to address these issues. Of course, the study of variability in its own right is important. Up here, the variability is a sort of secondary issue. The prime interest is estimating the mean. But of course, you have to come to terms with the variability. Whereas in these contexts, genetics, early work in the 30s, industrial statistics, that's the context in which Daniels wrote his paper. Agriculture, of course, an understanding of the variability in its own right is the object of the exercise. A third area, what I've called here the efficient estimation of fixed parameters. This is slightly different. You might think that the estimation of a population mean more or less is subsumed under this, but there's a somewhat different emphasis there. The combination of information in block experiments, where the blocks are incomplete, of course, is a situation where you do that. This would be one where you have to come to terms with the variability before you do the estimation. Incomplete, sometimes extremely incomplete multi-way tables in animal genetics, animal breeding, where you have a whole pile of effects, some of which are sometimes regarded as fixed and others random, size. Other situations in agriculture where you're measuring certain varieties in experiments in different places over different years. Coming to terms with what's happening there, for example, getting estimates of variety effects, which are appropriately averaged over sites and years. So all of these things are pretty standard, but I mention them simply to ask the question later, do we need or is it necessary to embed our analysis of these problems in the so-called normal independent model, or are there other ways and are there other benefits? And finally, I mentioned a topic which you'll see from the program is going to be addressed by Professor Rao later in the week, prediction of unobserved random variables. For example, the yields of future daughters of a sire in animal, for example, in dairy cattle. So they're the sort of problems that I won't be addressing in any detail. Most of what I'm saying today is just words, but if you want equations and symbols, you'll be able to get the references in the paper that I've written for the conference. Okay, so I start off. That's not starting off. I'm pressing on. Why generalised models? Well, first I explain that the word model I mean here a dispersion model for the usual multiply indexed arrays. So they're the models I'm talking about. You can get them by postulating random effects You can get them by other ways, by defining a full distribution. I'll mention some of them shortly. Why generalised? Well, the concept of generalised I'm using here means getting beyond normality, beyond additivity. I'm sorry to say that I'm not getting beyond symmetry, in the sense that the labels on the effects are regarded as irrelevant. So there's a lot of symmetry in this, and that's certainly a criticism of the generality of what I'm saying. But, I think if one didn't make some sort of restriction, it'd be very difficult to say anything. So I have to keep that set up. Okay, for the full story, read the papers. Okay, what's the full story? Well, I want to briefly mention why generalised models. Well, if you go back to the late 50s and early 60s, when this work had essentially been completed, there was a nice review paper by R.L. Plackett. All of these references will be in the paper that you'll subsequently receive, so I'm not going to give details now. The model should more accurately reflect the experimental situation, was Plackett's remark. And it's worth hearing the rest of that remark, actually. I rather like it. Rather than simply supply conditions under which the classical tests remain valid. In other words, think about what you're doing. Don't just make a model because it happens to be one that you're able to analyse. And that's a very telling criticism, I think, of a lot of the uses of variance components or analysis of variance these days. Cornfield and Tukey elaborate slightly. They mention that the assumptions, that is the models that you're assuming, should depend on the nature of the sampling and the randomisation involved. These are words that don't get an opportunity to appear in the normal linear models that we're talking about. Randomisation doesn't have a place in standard analyses of linear models, and neither does random sampling from real populations. Kempthorne and Wilk repeat some of the same points. The above points are emphasised, and they comment that normality and independence are unrealistic. I mean, a standard example might be the idea that the interaction between two factors should be independent of the main effect, which in reality is rather absurd, because it's a very common experience that large effects have large interactions, and that violates this simplistic idea that we have a nice additive independent component. Of course, Kempthorne and Wilk were very interested in randomisation and what they called the experimental situation, and again, this doesn't have any place in the standard treatment of variance component models. You realise that I'm going to get you all excited thinking, well, what is the answer? And then it's going to be 2 o'clock and we go on to the next talk, and then sometime later in the year you'll get the copy of the paper. I'm sorry about that, but well, that's it. 1 half an hour talk. Oh, that's a thought, yes. Anyone come from the Arctic Circle? Love to go up there. Is there a University of, what is it? Oh, that'll be right, yes. Okay, so let me briefly comment on what I mean by a component, or what is a component of variance. And I said there's no mathematics here, so I'm in a simple situation that I call between within. In other words, there are some sort of groups and some sort of units within the groups. For example, blocks into plots, or sires and their daughters, or trees and their leaves. So the question that I want to address, very briefly, of course you can guess the answer, but let's have it. Is it necessary to assume this sort of model, the model that you see in, I won't say all the books, because there are a lot of eminent authors of books in this room, and I'm sure some of them don't do this, but is it necessary to assume that the observation for I labelling the betweens and J labelling the withins should be a constant mean plus a random between effect and a random within effect, where these are normally and independently distributed with their own little variance, and they're independent? Is it necessary to assume all that before we know what we mean by the between and within components of variance? In other words, do they have to be these things within that model? Because if so, then there was something wrong with Fisher, Yates, Neyman, and all these other people I mentioned, because none of them used that model. So the answer is emphatically no, we don't have to assume that. And I'll now give you a small framework within which we can do many of the same things without assuming a model. Now, of course, this is assuming a model 2. It's just a rather more general model. So let's replace that model NAM for normal additive model by this one here, FDM, which is an abbreviation for the term factorial dispersion model, which is in the abstract, so I've now told you what it means, but I won't define it anymore. So this is simply saying that there is some correlation structure in our observations. Now, it's not unlike the correlation structure induced by such a model. So there's nothing terribly radical about it. There's a common variance. There's a common covariance for things within the same group, for daughters of the same sire or for plots within the same block. And there's a common covariance for all the rest, which is quite frequently regarded as 0, but it doesn't hurt us one little bit to leave it as non-zero. And in a permutation model, it's there. So we might as well leave it there. Okay, well, that situation, that model FDM, allows us to include the permutation distribution obtained by randomly relabeling or randomising your labels of, say, blocks and plots, which, for example, if you're interested in doing what Pittman and Welsh, or Welsh first and then later Pittman independently did, which was look at the randomisation distribution of certain key statistics, they were doing it with a correlation structure of that form, not one of that form. Random sampling, which was put into this framework probably most effectively by the Tukey and Cornfield paper, where you have a number of groups that you sample, and then within the groups you sample units, and the probability model is the sampling structure, not something you just assume, but it's the random sampling. When is he going to take the photograph? I'm sorry, I hope I don't put you off. Thank you. Right. Okay. And finally, this also includes a framework which I call generalised or partial exchangeability. For the Bayesian aficionados here, already in the 30s, De Finetti looked at exchangeability with 2 or more indices. Where, and here by this I mean that you have exchangeability within the groups, and you have exchangeability, that's the invariance of the whole joint distribution under the permutations of whole groups. So it's not hard to see that such an assumption would lead to a covariance model of that form, as well, of course, as the normal additive model. So the answer, I say, is no, and we have to see what we mean by a component of variance, and can we address the problems. This is the hard piece of the talk, I think, at least in the sense that it has a bit of content. So here meaning on the last transparency, the J, that's the label of the unit within the group, is within I, 1 to m, and this observed array may be part of a larger array. What I mean by that, for example, in the sampling model, you may have a large number of things that you could potentially sample, and you sample some of them. And what you see then is, in the obvious sense, a sample from a population. So there may be capital M groups, each of which you have capital N units, and you sample small m on small n. Now, just a brief comment about the parameters. The parameters in these models I'm talking about are initially the variances and the covariances, which are definitely not what people regard as components of variance. One of the things that I'd like to suggest is that you might have different parameters giving meaning to different questions in different situations. And it doesn't all have to be expressed in terms of sigma squared between and sigma squared within. Now, just a little comment about some mathematics now. This is the only mathematics in the talk, unfortunately, but we don't have much time. So I'm just saying here we can define, with that covariance structure, with FDM, a linear thing which I'll call a linear decomposition. Now, it's not a very surprising looking decomposition because everybody who does analysis of variance knows it. But thinking of these things as random variables, these 3 bits are uncorrelated. That is to say, they're uncorrelated under a covariance matrix of the kind I described. And of course, they look like they're pretty good candidates for between and within components without having had to be postulated to exist. They're there already, implicit in the covariance structure. And I make the comment that they've... Oh, that's a spelling mistake. Terrible. That's what happens for getting up early in the morning in a foreign country. You forget that you can speak English. Okay, that should be T-H-E-I-R for any people that want to speak good English. Maybe I should do it now before I get photographed or something like that. Oh dear. How could I do that? Excuse me. How's the television camera? You got that? Okay, so their variances add. So that's definitely an analysis of variance already, although in general these components here for different I or for different pairs I and J would be correlated within these, but that and that are uncorrelated. Now I make the comment here that if M or N or both can be extendable, that is to say we do have a broader population, these dots can be conveniently replaced by averages over the broader. And I give an example here where we suppose that N could be anything up to some number capital N, which may be infinite. And then you can actually, I replace the dot by a dash. Now this is a sort of a population average. Although this looks a bit bizarre, it's quite a useful idea, and it is implicit, or actually it's rather more explicit, in the Cornfield-Tukey paper. Although they're only concerned with sampling models. They don't look at the abstract framework. So, and if anything is infinite, all these things exist as mean square limits. Now that's to say that simply from that covariance structure alone, we can have something which is rather like the linear model, and it's going to do just as well. And I'm not going to be able to elaborate any more on that, just that you don't need to assume it. It's part of your symmetry assumption, if you like. And the virtue of that is we've captured the essential parts, at least the second order parts, of all of those models, the randomisation models, the sampling models, the permutation models, and so on. Just another comment here. Again, a little mathematical comment. Everybody that has ever done the most elementary analysis of variance will have seen that object there, the so-called within group or within class mean square. And if I am prepared to make the generalised exchangeability assumption, that sort of thing exists. Well, obviously it exists for all finite M and N, and it actually converges to something which ought to be a suitable candidate for the within group mean square, within group variance component, even without any further assumptions. So I guess the moral here is that with only this factorial dispersion model, most notions carry over and permit perfectly satisfactory inference within the broader or within the desired framework. Now that's simply putting together the elements of the work of all these people in the 30s and 50s that I mentioned. Time running out. I'm on to my second last transparency. Don't panic. Well, old approaches to old problems. I say, can the problems in the different application areas be discussed or solved within this framework? Well, in theory, of course, it should be trivial because it includes the ordinary variance component model. But what I want to say is that you don't even need to specialise. The notions that all the notions you need to address these problems are there, and you don't need to postulate a random effects linear model. And I say that in a way that is precisely what these earlier writers were doing. So it's hardly a new observation. But, see you later, has to be a but in any categorical assertion, and we'll get to it. Now, I've got here that it might be of interest to develop a unified or a general approach with a common body of results. In other words, whereas Cornfield and Tukey worked with sampling models and other people, Kempthorne worked with permutation distributions, most of the world work with random effects models, and a few Bayesians hammer away with generalised exchangeability concepts. Let's try and do it all in one hit. And attempts to do this are underway, and I mention a collaborator, Rosemary Bailey, in particular. You don't know et al., so I won't mention his or her name, but they're not statisticians. Okay, see, I've just given a very simple example here. I know time's running out. But suppose you want to estimate a population mean. Well, it doesn't require the normal additive model. Neither do any of these things, as I assert there, but just a totally trivial observation. From the covariance matrix I've got, one can very quickly derive this expression, which says that the variance of the overall of the sample mean is something divided by all the total number of observations something else divided by the number of groups, and something else again. So one can easily get insight into how to optimise the choice of sample sizes between and within without postulating a model of random effects. I mean, and of course, in this context, we really aren't interested in the random effects. We're interested in this optimising. Just another little thing I'll have put there, if there is time. A very early paper, 34 or 35, by Yates and a colleague at Rothamsted, looked at the efficiency of sampling rather than totally harvesting plots in an agricultural environment. And again, well, they had a model which permitted competition. So that's negative association in plots, which you can't get with the ordinary additive models. But their results fit into this framework perfectly satisfactorily. I can see that this timing is perfect, so I'm not going to have any extraneous words. Yet another example, we can do finite population prediction quite satisfactorily. If you want to think of our groups as perhaps the offspring from sires, we might have sample of small m sires from capital N, and each of these sires has a potentially very large number of daughters owing to artificial insemination. So we might have a small n from there. And you're typically interested in a BLUP, a best linear unbiased predictor of the so-called CSIRO effect, this thing, where that is an average over all the daughters that the bull may have in the future, and the ones in the present up to now. So it's not an estimate of a fixed effect, it is an average of a random variable which involves unobserved observations. And it comes out rather easily to be that, which, with a little bit of algebra, very quickly simplifies to a very familiar formula. This thing here, I've just put it in the notation where these F's are in terms of the covariances, and finally I'll put it there in terms of intra-class correlation. This is a very, very old formula to tell you how to estimate, if you like, the future productivity of, say, a bull or a pig or something like that on the basis of its offspring observed to date. So the moral of this little sequence, which I regret I haven't had time to give it much detail about, is that all the standard problems that one wants to address with, this is in practice. I'm not talking about mathematical problems. I haven't mentioned F-tests, I haven't mentioned distribution theory, because I haven't assumed any. So that's another story. But in terms of estimating things that you're interested in, it can all be done at this level of generality. And my final catch is that this was the but of before. And I want to sort of end with a bit of a challenge to myself and other people. The only general algorithms for estimating components of variance for so-called unbalanced data. I haven't told you this, but all of the things that I've said work nicely if the data has this property called balance, which is hard to define, but we all know when we see it. So it's basically that groups are all equally sized and so on. So beyond that, it seems that maximum likelihood methods are about the only ones available. So generalising these ideas to normal but more general dispersions is probably okay. Going beyond normality is the challenge that I would like to leave, as I say, myself and anyone else interested in pursuing this. Beep, beep.